All right, so let's get down to business. Last time we had a look at a new section on integration. And we looked at these two, well actually we looked at two new things and one thing that you should have already known. We looked at integrals of trig functions and so-called reduction formulae. Now with trig functions, it's just a matter of playing with the integrand, okay, the actual thing that you're integrating, perhaps pulling out a sine or a cosine depending on the powers involved. And for the reduction formulae, can anyone sort of boil that down, the techniques, to a few words? Anyone? What? Integration by parts, that's right. So today we're going to continue our look at integration, and we're going to have a look at these two parts, so trig and hyperbolic substitutions and partial fractions. Now, some of you may have seen those before, that's fine. If so, that's great. If not, don't worry about it. All right. Now, at school, or possibly in first session, you looked at integration by substitution. So essentially, the idea here is to take some sort of difficult integral make a substitution and pull out an easier integral, right? If we've got something that's challenging or difficult, what a substitution can do is make things a little bit... Man, can you? Thanks. I don't like iPods, so... Or what is it? Is it an iPod? What is it? Or you just listen? Oh, is it just for that? Okay, all right. Because I see, and I'm like, oh, he's only got one ear. Oh, no. I want both. I want both. Anyway, in this theorem, basically, it's just making a substitution, u equals g of x in there, okay? It's essentially just running the chain rule backwards. That's all it is. Now, for integrals involving square roots of quadratics, what we do is we use a trig or hyperbolic substitution. Okay, now some of you again may have seen this before. So, now before we get to that though, I actually want to show you an example of where these things crop up. Do I have one? Here we go. All right. Now, why and how would you want to integrate something involving a quadratic and a square root sign? Well, that's a pretty good question. Imagine that you have a piece of wire that when laid out in the xy plane, it just traces out the curve y equals x squared on 2. Now, one of the basic problems in engineering, applied sciences, physics, is to calculate the mass of a given object, right? In this particular example, you've got a mass with constant density in mass per unit length. What you do is you basically can use this representation here involving the derivative, and we'll actually learn where this comes from later on in the session, probably about week 11 or week 12. So you will see this stuff again. So essentially all you're doing here is differentiating this and squaring it. If I differentiate, I get x, and then I get this square root involving x squared. The density is just constant, so I can pull it out the front. So here's a an example from physics where you actually need to be able to integrate these things with square roots. Okay, so that's one small motivation for this study. So here's a table that I've put together, sort of as a reference guide, really. You may already know all these things. If so, that's great. But depending on what your integrand, or depending on what your integral involves, you can use a different trig or hyperbolic substitution. Now, when you make a substitution, of course, you need to calculate the corresponding differentials. Okay, so I've written, sorry, that should be a dx. I've written down the corresponding differentials for each of those substitutions. Okay, in here, a is just a constant. So this is a good little reference table that you can refer back to until you've got these things down pat in your mind. Okay, so we're going to look at a few examples, and I'm just going to illustrate to you how these things work in practice. So let's solve some examples and see how this all works. Before we get to that though, essentially when we solve these problems, we're using a little bit of trig, and these triangles are going to be important. Now, usually what I do is I construct the necessary triangle when I do the problem. Okay, and another important idea that we're going to use are some of these identities. Now, I can't remember all those identities. All I really need to know is the first one, cos squared plus sine squared equals 1. Okay, you can get the other two from that first one just by dividing by cos squared or sine squared. All right, so let's do an example and see how this works. So we'll come back to that in a minute. All right, evaluate this definite integral here. So you can see our integrand involves root 16 minus x squared. So if we look back at our little table, you can see that we're going to try something like x equals 4 sine theta. Now, even if you've learnt this stuff before, and you go, come on, Chris, I know this. You may have not been told all the ins and outs of it. So, for example, the theta here is between minus pi on 2 and pi on 2. Can anyone suggest why that is? Yes, up the back. Excellent, yes. Okay, this isn't taught at school, for example, or I don't think it is. It's important where your theta, like some bounds on your theta, because sine inverse doesn't exist everywhere. So you've got to restrict the theta to where sine inverse exists. Very good. Okay, so that's a small thing. So the dx is going to be 4 cos theta d theta. So because this is a definite integral, I'm going to change the limits of integration as well. Okay, so if x equals 0, what's theta going to be? Zero, right. And for x equals 4, theta is going to be pi on 2. Good. So we've got all the elements now to make our substitution. Hopefully, it's going to be simpler. So let's call this star. So we replace dx with this, x with this, and the limits of integration. So we're going to get 16 sine squared theta times 16 minus 16 sine squared theta times 4 cos theta d theta. Now, you may look at this and go, Chris, you've just contradicted what you said at the start of the lecture. We're supposed to make these things simpler. Come on. Well, yeah, I agree with you. It's a mess. But can we make it simpler? First of all, we can go to town on that square root sign, right? That's a good start. Let's try to do that, right? So what can I replace 16 minus 16 sine squared theta with? Yeah, 16 cos squared theta, right? And then take the square root. So if I factor that out, well, I guess if I, let's just do it. All right, so now I can eliminate that square root sign, and I'm going to get something like sine squared theta times 16 cos squared theta, right? Now, when I'm taking the square root sign there, technically I should have absolute values. Can anyone tell me why I can ignore the absolute values?
Because it's going to have the same value as what that would be.
Absolutely, right? Again, it comes back to this little thing. Cos theta is positive there. Well, non-negative. So I don't need to worry about the absolute values. Yes? Yeah, but it's 16 times 4 times 4. Is that right? Okay, good. Okay, so now what? Now I've got one of those examples that we kind of looked at in the last lecture. Well, what I'm going to do here is use double angle formulas. So I'm going to combine that sine and cosine into the following. Okay. So all I've done there is I've used a double angle formula, which I have to square. All right, well, expanding this square, I can get the following. We're almost there. Anything I can do with this sine squared 2 theta? Does someone say double angle formula? Yes. We're going to do a double angle formula involving 2 theta. So the 2 theta is going to go to something involving 4 theta. Okay, so you may be thinking, come on, Chris, this is a lot of work. I haven't done the integration yet. Well, we can do that now. All right? We've done all the necessary groundwork to do the integration. All right, so when you integrate 1, you're going to get theta. When you integrate minus cos 4 theta, you're going to get something like minus 1/4 sine 4 theta. Okay, so all you need to do now is do the substitution. You're going to get 16 pi. I won't bore you with all the little details. Okay, so where does that rate on the difficulty scale, as for example a class test? Is that more than what we expect, less than what we expect, or just right? I reckon it's, well, I'm going to give you an example that I have seen on a previous class test. So it's just right. It is a bit of a shock to the system, I know, because there's about 5 or 6 lines there, but it's a good standard. Okay? Any questions for that particular example? All right. All right, this one, this is the example that I just mentioned. This is a perennial favourite on class tests here. Class test 1. The A here is a constant, and people, for some reason, fall over on this question. It's not that difficult, so let me show you how we do it. All right. So we have an integral involving a squared plus x squared cubed with a square root sign in it. So we're going to let x equal a tan theta. Okay, so we're going to restrict our theta to this interval just to keep things all nice and well defined, and the inverse exists. So if x equals a tan theta, what's dx going to be? A sec squared theta d theta. Yes. Now there's no limits of integration to worry about, so it's a little bit more streamlined. So let's just substitute in. All right, so the top is going to be replaced with this, and the bottom is going to be something like this. Okay, so what we would like to do now, it's looking a bit messy, but what we would like to do is simplify that denominator somehow. Well, I can write that in terms of sec squared theta, right? So the bottom is going to go to a squared sec squared theta. So now all I need to do is cancel off. Don't need to worry about absolute value signs because of the restriction of theta, so you can just ignore that. So I'm going to get something a little like this. So we're going to have a cubed on the bottom and sec cubed on the bottom. So now I can just cancel. Almost done. What's 1 on sec theta? Cos theta, yes. So this is even simpler. So I integrate that to get sine theta plus a constant. All right, so I've done the integration, great, we're very happy. But what I would like to do is get the final answer in terms not of theta, but in terms of x. We started with x's, let's finish with x's. So I can either refer back to the triangles that I showed you in the earlier slide, or I can just draw my own triangle here. Okay, x equals a tan theta. So tan theta equals x on a. So tan is opposite over adjacent. So all I need to do to work out the hypotenuse is use the standard Pythagoras theorem. So from this right-angled triangle, I can now calculate sine theta. All right, so what's sine theta going to be? It's opposite over hypotenuse, right? So x on root x squared plus a squared plus the constant of integration. Okay, so that's what we would expect in a class test. We've done it before. In my experience, the place where students fall over in this problem is not with the integration, it's with the algebra. They don't know the index laws or the power laws, okay? Believe it or not. Sometimes the most common mistakes are the simplest. Questions? Yes?
How do you know that? Where do you know where the A's and X goes on the triangle?
Oh. Well, it doesn't matter, right? I mean, hang on. So I beg your pardon. Let me rephrase that. If the theta's down here, right, then I've fixed theta. So once I know where theta is, it has an opposite and adjacent, right? If the theta's up there, then you just reverse it. Reverse x and a. Okay? That's a good question. Any other questions? All right. Anybody notice anything a bit different about this lecture? What's missing?
Camera.
Yeah, there's no camera. Let me tell you about my woes. That crazy thing down the front that I'm stand behind, it records at a certain frame rate, right? Frames per second. The one at the back is a different frames per second. So I'm sitting in there I've got the two things on the editing program. I'm trying to link them up, right? But they go at different rates. So this thing, I'll be standing over there and suddenly my hand will go, whoop. So it's been bugging the hell out of me, and I can't. So everything is going through that now. So you won't see, my ugly mug, but it'll be easier to produce these things. Anyway, that's why we don't have a camera today. So I'm trialing it for today. Who has had a look at the ones I've posted from last year? Anyone? Yeah, good. Okay. All right. Here's another example. In this particular example, we're asked to calculate this integral where x is strictly greater than 1. Again, this is just so the inverse of the functions that we're using exists. So just think of that as making everything well defined. Okay, so if we make the substitution x equals sec x, and in this case I'm going to have theta between 0 and pi. So if x equals sec x, what's dx? Anyone? Shh. So if x equals sec x, what's dx? Yeah. D theta. Again, it's a definite integral. There's no limits of integration, right? So let's make our substitution and see what happens. Let's see what happens. Okay? All right. All right, so we're going to have sec theta, tan theta, d theta up the top. Down the bottom, I'm going to get something like this. Now, I can manage the square root sign away just by replacing sec squared minus 1 with tan squared. And because theta's in this range, tan is positive, so you don't need to worry about the absolute values. So I can cross off one of these secs straight away. And lo and behold, I can cross off another set of tan thetas. So what I'm integrating basically cosine theta here. So now all I need to do is get my final answer in terms of x. It's a little bit more, I guess a little bit more difficult here because x equals sec theta, so x equals 1 on cos theta. So if you rearrange that, cos theta equals 1 on x. Okay, so if that's my angle, cos is adjacent over hypotenuse. And then to work out this third side, again, you just use Pythagoras. So from that little right-angled triangle, I can calculate sine theta. Opposite over hypotenuse. Okay, so can I have a show of hands? Who's seen those kind of problems before? Who's pretty comfortable with them? All right, okay. All right, a few people. Good, I'm glad. Yes? Yes?
Isn't x is only values x cannot be x equals 0 and x equals 1 and minus 1. Other than that, it can be that.
Sorry, say again?
So x equals 1, x equals minus 1.
No. X is not, because look, x is strictly greater than 1. You see it? So I've just built that into the problem. Okay? That's a valid point, though. Valid point. Okay, so learn those techniques. I almost guarantee you, not a money-back guarantee, that a large proportion of class test 1 will have something like that. That second example is gold. Yes? I wouldn't assume it. Okay? Oh yeah, I wouldn't assume it. If they're being nice, they won't. If you're unlucky, it's a possibility. Yep. Okay. So the second half of this lecture is going to, we're going to talk about the method of partial fractions. Who's heard of the method of partial fractions? Okay, just a few people. That's all right. Now, we are going to look at integrals of the following form. You have one function divided by another function where both of those functions are polynomials. So x squared plus 1 divided by, I don't know, 2x minus 1. They're both polynomials. If we have this polynomial set up, then we can apply a pretty important technique called the method of partial fractions. Okay? So essentially, you're given a difficult integral, you apply this method, and it allows you to integrate the problem. So this, you see we've got a polynomial up here, polynomial down here. That's a rational function. That's not. That is. That's not. Okay? So Now we're also going to assume that the degree in the numerator is less than the degree, well, I guess the highest degree in the denominator. So you see how up here the highest power is x to the power 1, whereas down here the highest power is squared, okay? Whereas here it's reversed. We're going to look at these kinds of functions and their integrals, okay? All right. So let's just think about this particular integral right here. I can't integrate that by inspection, can you? It's a hard integral. However, we can break it up into two integrals that we actually can compute, right? And the question I've asked on this slide is, can we write our integrand, the thing we're integrating, as some linear combo of two things that we can integrate? And the answer is yes. Let me show you. How can I turn this into a linear combo, just a combination of these two things? Well, there's a fast way and a slow way. The fast way, and the way that I absolutely recommend that you should look at, is to play with the numerator, that one on top. Make that one on top something like either this function or this function. Right? Let me show you what I mean. If I take an x away and add an x to the top, I haven't changed it at all. If I break that up, then we're going to get some cancellations. Watch what. So I can cancel this with this and this with this. That's pretty easy. So even if you know partial fractions, don't be blindly misled into applying a method that's absolutely not needed. Okay, it's like using a sledgehammer to crack a nut. I can just play with that numerator and get exactly what I want. Okay? So this, I recommend that you should look at this for all the problems you do first. See if you can play with the numerator. Of course, that won't always work. Now, here's a big mess of partial fractions steps and tips. I'm not going to concentrate on the general method. I'm actually going to show you specific examples because I think there's more benefit in those. Okay? I do want to share a little bit about the following method called the Heaviside method. Anyone heard of Heaviside? Oliver Heaviside? Ah, well, I'm glad you asked about it. I'll come back to this. Here's Oliver Heaviside. Oliver Heaviside was an engineer and an applied mathematician. And you might have heard of Maxwell's equations on electricity and magnetism. If not, you may see them during university study. Maxwell's equations were originally 20 equations in 20 variables. There, it's not very friendly. So Heaviside came along and boiled them down to 4 equations in 2 variables that are still more or less used today. Anyway, Heaviside was a bit of a rebel, really. He used to have arguments with all sorts of people because he would just sort of do stuff without formally justifying it. And a good one was a couple of good quotes here. mathematics is an experimental science and definitions do not come first, but later on. In other words, what he's saying is you do the experimentation first, and after you've experimented and played around a bit, then you actually go back and really precisely define things. Which I believe that. I absolutely believe that statement. And secondly, why should I refuse a good dinner? Simply because I don't understand the digestive processes involved. That was his reply when he was criticised before formally justifying the use of operators. But he would use them anyway. He was a rebel. Anyway, let me show you how the Heaviside method works. One of the first steps in integrating this problem is to actually realise that you can factorise the denominator. So that gives you a clue straight up on what decomposition you're going to have. So I'm going to say that I can write this in terms of a constant a on x plus 3 plus another constant b on x plus 2. So what I would like to do is find those constants a and b and then integrate them. The integrals are going to involve logarithms or something like this, right? So that's the challenge. Can I find constants, big A and big B, that satisfy that? Well, yes, I can. So we're going to assume that 2x minus 1 over x plus 3 times x plus 2 is in this form for some constants, a and b. So what is the Heaviside method? What is the Heaviside method? Well, it's just a little game. You just cover up parts of that equation, basically. So let me show you how it works. To find A, this is important, you need to listen now, right? To find A, what I do is I look at what's underneath it and go to the left-hand side. I cover up that x plus 3, right? And then substitute in x equals minus 3. That'll give me A. All right, so I go to the first one, look underneath it, the first constant here, look underneath it, x plus 3, go back, cover up that bracket, and substitute in x, so I'm ignoring this, and substitute in x equals minus 3. That will give me the value of big A. So let me just write that out. All right, so I'm going to cover up x plus 3 and substitute in x equals minus 3. So on the top, we're going to get minus 6 minus 1 over minus 3 plus 2. 7. That's pretty easy. Okay, so to get big B, you just go here and cover up the other one and substitute in x equals minus 2. 8. So in this case, if I cover up x plus 2 and sub in x equals minus 2, I'm going to get the following. Big B equals minus 5. That's it. Go Heaviside. That's it. Okay? So now I've just got to do the integration. So we're going to work out these integrals. And we're going to get something involving logarithms. Now you can, of course, bring those logarithms together if you wanted to and simplify. I'm not going to do that. Right? Heaviside, pretty cool, huh? Those of you who know this method, is that the method you guys learned at school, or no? Method of undetermined coefficients. You multiply out and then compare the coefficients of the squares and stuff. What about you? Is this the way you learn it? Something else? Yeah. Can you see how this is faster? Possibly faster. I'm not dissing your method, okay? I just like Heaviside, okay? That's pretty good. The best thing about that is there's virtually zero algebra, okay? That's what I like about this method. There's almost zero algebra. That won't work every time though, okay? Won't work every time. All right, so here's another one. What I'm going to do is assume that I can break up the integrand into 3 parts because I've got the 3 factors. So for some big A, big B, big C, I'm desperate to calculate their values. So can we use the Heaviside method here? Yes, we can. Yes, we can. All right. It's just a little game of cover-up. That's all it is. So I'm just going to go straight to it now. All right, so if I cover up, so just ignore the integral sign here. I'm going to cover up x minus 1 and sub in x equals 1, top and bottom. Okay, so on the top, I'm going to get 2 plus 2 plus 6 over 2 times minus 1. So all I need to do is simplify that. Minus 5. How easy is that? So let's go over to the next one. Let's calculate b. We cover x plus 1 and sub x equals minus 1. So I cover up that middle one and substitute in x equals minus 1. So I'm going to get 2 minus 2 plus 6 on the top, and minus 2 times minus 3 on the bottom. All right, and the last one is C. So we're going to cover x minus 2 in our integrand and substitute in x equals 2. Okay, so we're going to get something like 8 plus 4 plus 6, 1 times 3. So if I work that out, hopefully I get 6. Okay, so all I've got to do is do the integration now, which is going to give me some logs. So let's call this I. So each of these three things are going to give us a logarithm each. That's it. How good's that? Now, if you use the method of undetermined coefficients there, it'd take you a bit longer, I reckon. Yes?
Are those absolute value signs or brackets?
Absolute values. So these are absolute value signs here.
Why do you use them there though? Brackets.
What's that?
Why do you use them there instead of brackets though?
Because when I integrate, right, I'm not sure whether, for log to be defined, right, okay, you really should have the absolute values here, because you don't know whether x is, x minus 1 is positive or negative, okay? Any other questions? All right, Heaviside method, really good. Now, on some occasions, you'll come across what's known as a repeated linear factor. So you can see in that integrand on the bottom, I've got x plus 2 all cubed. In this case, the decomposition is not quite what you would expect. So this is an important special case. So I'm going to claim that it's the following form. This is important. Oh, no, squared. Okay, so you can see how these powers of x plus 2 are increasing up to 3 in this case. Now, on first inspection, that decomposition looks really odd. Why isn't it just a on x plus 2 plus b on x plus 2 plus c on x plus 2? Why not? I'm confused. It's not general enough. Let me actually show you why this is the way to go. Now, it comes down to common sense, okay? Can you see how I can break this up to get something like x plus 2? I can break it up, yeah, I can break it up into x plus 2 plus 1 and then break that up, okay? So, okay, so I can split this up. Cross, cross. It's a cubed in here. Okay, so 1 on x plus 2 plus 1 on x plus 2 all cubed. Now, I can integrate that straight away. I can integrate both those terms straight away. You don't even need to do partial fractions for this problem. Oh! Oh, squared, yes. Hopefully I know my algebra. Thank you. So even this, more correct version, I can still integrate. Okay, so this is an important common sense rule. Don't use partial fractions unless they're absolutely necessary. Okay, they're not that much work, but just simple algebra can get exactly what you want in a fraction of the time. Okay? All right, I will discuss the rest of this problem tomorrow.